Alrighty, this is the Unit 10 review. I gotta go through this quickly, so just make sure you're paying attention so that you are good to go. You can always slow it down if you need to. Okay, the first problem says to go ahead and write each logarithm in exponential form, so make sure that you read your directions carefully. And this is the problem because it's in exponential form, we're gonna use the e. So you start with the 9, and then it's going to go to an exponent of 2 and come around to 81. And you can see that e. So same thing here, 13 to the second power equals 169. 2 to the negative 3 equals 1/8. And then 144 to the 1/2 equals 12. Okay, this is just converting. It is not having to evaluate or simplify, so just let it be when you're done with that. Okay, the next one says write each exponential expression in logarithmic form, and log starts with an L, so that's what we're gonna do. We're gonna start with the 11. So of course, actually, we're going to start with log because if we're writing it in log form. So if you want, every time it says write in log form, you can just start with log. And then the base of the exponential is the base of the logarithm. Then we're going to get the argument, which is 121, and then come back to the square. Logarithms always equal that exponent. So if the L isn't your favorite thing, if you can see right here, this is like a block L, you can always just set it up like this. The base is 4 of the exponential, so the base is 4 of the logarithm. Logarithms equal the exponent. This exponent is 2, and then the only other number is 16. I'm going to stick with the L. So log base 81 of 9 equals 1/2, and then log base 5 of 1/25 equals -2. Okay, so moving right along right here, now we're asked to evaluate, which means give a value for what we're doing here. So whenever we do evaluate, we set these equal to x. And then we're going to go back and we're just going to translate them to exponential. Logs and exponentials are inverses or reverses of each other. So they're partners in crime and math. So I'm just going to go 5 to the x equals 125. Okay, 125 is 5 to the third power. And because the bases are equal, the exponents must also be equal, so we can clearly see that x equals 3. 7 to the x equals 1. What power does that exponent have to be for 7 to give me 1? Anytime the argument of a logarithm is 1, that exponent must be 0. Now we have a fraction in our argument. So again, 4 to the x equals 1/16. Well, let's be smart here and pick to write 16 as 4 squared. And then because it's in the bottom and this guy isn't, we want to move it up. So that would be 4 to the x equals 4 to the -2. So anytime we move it up, it becomes negative. So that means that the exponent that will make that statement true is -2. Again, logarithms equal exponents, so that's why it's that. 7 to the x equals -49. I'll tell you right now, this is undefined. Anytime the argument of a logarithm is negative or 0, the logarithm is undefined. Here's a quick reason why. 7 to the first power is 7. 7 to the second power is 49. Both these numbers are positive right here. Okay, let's get smaller then. That's 1. 7 to the -1 is 1/7. 7 to the -2 is 1/7 squared, which is 1/49. you can see none of these numbers are negative. So that means that there is no exponent that's going to give me a negative argument. So that means log base 7 of negative 49 is undefined. Let's go to this guy, 36 to what power is 6. So I can see that I can rewrite 36 as 6 squared, and then I'm going to bring down that x. And this is 6 to the first power. So now because they have the same base, using the property of equality, the exponents must also be equal. So I'm not dividing out that 6. I'm just using logic and saying, hey, there's an equal sign here. If these parts are already equal, then the top parts must also be equal. So that means 36 to the 1/2 power equals 6. Alrighty, let's move up to the top here. Expanding, and then we'll be condensing. So you might want to write this at the top of your paper just to help you out here. If you are multiplying when you're in condensed form, then when you go to expanded form, you should be adding. And if you are dividing in condensed form, then you're going to be subtracting. And keep in mind, dividing in math also entails fractions. Okay, so let's analyze what we've got going on here in 4a. First of all, what I want you to do is change this to log base 3 of a squared over b squared. It's going to make your life easier. And as you can see right here, we've got a fraction bar. So we're going to be dividing. And then we also have two bases in that argument. We have a and we have b. So the first step is to write log base 3 of a squared minus, again, that minus is because of that division or that fraction bar. And then we have the bottom one, log base 3 of b squared. So when you expand, every base that you have in the argument needs to get its own logarithm. I have a base a and a base b, so that's why I have 2. And then the other rule that we learned about is that if you have a power right here, it needs to come down in front. And there's a power here too, and that means multiply. So you're just going to multiply it to the front of that logarithm. You will know you're done with expanding when you only have just a letter or a number in the argument there. Okay, not more than one. Next one, we're going to notice that we have multiplying going on here. And notice that we don't have an exponent outside here, so we don't need to shower the power like we did with this 2 up here. Okay, so we have a base of x and a base of y, so that means we're going to need 2 logarithms. So log base 4 of x to the 5th and log base 4 of y to the 4th. What goes in between? Well, because we are multiplying between them, and we already wrote down, if you are going to expand, multiplying goes to addition. So that is what we're going to do here. This is going to be just a plus sign right there. We look like we're done, but we're not quite done because, again, when you're expanding, you don't want these baby exponents right here. So what we're going to do is bring them down in front to get our final answer. So it's going to be 5 log base 4 of x plus 4 log base 4 of y. Okay. Moving on to that last one, we do have that power outside right here. So I'm going to shower the power. So that's going to give me log base 3 of x squared and y to the 10th. Keep in mind, guys, that if you're having trouble between deciding if that should be a 7 or a 10, then I would just suggest using the definition of being squared, which means writing it twice, and then you can see 5 and 5 makes 10. Okay, So you don't have to do that step unless you can't remember the properties of exponents. So now we see that we have multiplying going on here. So that means we are going to write log base 3 of x squared plus log base 3 of y to the 10th. And then we're going to use that exponent rule that says multiply it in front to get to log base 3 of x plus 10 log base 3 of y. And that's our final answer there. Okay, now we're going to do the reverse of that. So just the friendly reminder, looking back up at the top here, we were expanding. So we were going from a condensed form to an expanded form. So we were going this direction. Now we're in expanded form and we need to go to condensed form. So the rule is just reverse. So this says, again, to condense. So the first thing we're going to do is take that 6 and put it right there. Take that 4 and put it right there. So those are no longer there. Then we're going to take that addition and make it multiplication. And when we're condensing, it's to a single log. So we're just going to cross that out. Then we're just going to see what it writes. We have L, then O, then G, base 3 of a to the 6th times, all this stuff got canceled out, so it's just b to the 4th. And because mathematicians like to be lazy, they're going to not write that multiplication sign because anytime it's not written, it's implied. So that's just b to the 4th. Okay, same thing here. We're going to bring that up, cross it off so we don't get it confused. That 5 is going to go there. Then I'm going to change this subtraction to division. And I'm going to cross off this log because when you condense, that means make it smaller. Okay, and so now I'm just going to copy what I've written. Log base 4 of 8 to the 5th divided by, let's use a fraction bar instead of the division sign, and then b to the 5th. This answer is perfectly good. I think the answer on the back is going to be more mathematician approved, which means that they went ahead and said because both of these are to the power of 5, we'll just pull that power outside and put it up at the top. Okay, here we go with C. You end up feeling like you're doing the same thing over and over again, but that's great because that means that your brain has finally established the pattern that's necessary. So if it feels tedious after a couple, it's actually a good thing. All right, so we have log base 2 of a to the 6th. Because it was a minus, it changed to division. We'll use the fraction bar over b to the 3rd. That's it. Okay, this says solve the exponential equation using logarithms. So that's what we're going to do. So this right here is a logarithm with base, it's an exponential with base 9. So we're going to go ahead and take a log base 9 of both sides. And what that helps us do is that helps us isolate x. So log base 9 and 9 to the x, and 9 are inverses of each other. So we get log base 9 of 21. And that's our answer for the non-calculator portion. Moving on. This right here is e to the x. So what we're going to do is take a natural log or a log base e of both sides. So remember, in math, log base e, which is 4 letters, converts to 2 letters with natural log. Natural log and e, which is considered the natural number, are inverses of each other. So this just ends up being the natural log of x. Now we got a couple more steps on these ones. This is base 2. So what we're going to do is make sure that when we reverse base 2, we do it with the logarithm of base 2. So you can see what I'm really doing is this piece is here. And then I'm taking a log base 2 of both sides. So then 17 ends up here. And you can see that there's a log base 2 of both sides. That's nice because this log with a base 2 undoes that exponential with a base 2. So then I have m minus 5 equals log base 2 of 17. The n is not by itself yet, so I'm going to add 5 to both sides. When I do that, I'm going to make sure to put parentheses around the argument of the logarithm, because the 17 belongs to that log base 2, but the 5 doesn't, so they're not like terms, so I cannot combine them. Moving on. Oh, this one is also base 2, so I'm going to do that again. Log base 2 of 2 to the 9x equals log base 2 of 85. Don't try to shortcut this. Make sure you're doing proper form. That log base 2 undoes the exponential of base 2, and then I'm left over with 9x equals log base 2 of 85. Divide by 9 to get the x by itself. Again, we're reversing that multiplication. And that's the same thing. I believe the answer key says this. So dividing by 9 is the same thing as multiplying by 1/2. Moving on, I'm going to try and get these last ones done. This says, use the property of equality to solve each of the equations below. So it's telling you use the property of equality. It's not telling you to use a logarithm. So what we're going to do is see that we have this left side has a base of 9 and the right side has a base of 3. We need them to have the same base. So I'm going to change 9 to 3 squared. And then I have x plus 1 left over. Make sure you put that in parentheses because that means you have 2 terms, which means that distributive property is going to apply. Because we have 2x plus 1 equals 3 to the 5th. What we're saying now is because the bases are equal, this is that property of equality. We don't really need to focus on the bases anymore. We just need to focus on the let me reverse this a few steps because I just caught my mistake, silly goose. Right there. When I distribute, this is 2x plus 2. Not 2x plus 1 because that 2 gets multiplied to both the x and the 1. Those are irrelevant. And then we're just going to solve this part. Just reversing everything to isolate the x. So we get x equals 3/2. This last one, we're going to see that we need to write 32 and 16 with the same base. 32 is 2 to the 5th power. But then we have that 3x right there, also in the exponent. And then we see that 16 is 2 to the 4th power. Again, these bases have to match. Now that they match, we can just solve the exponents. 3x times 5 is 15x. And this side only has a 4. So we get x equals 4 over 15. Okay, and that's that piece. Okay, this says solve the exponential equation using logarithms. So that's what we're going to do. So this right here is a logarithm with base, it's an exponential with base 9. So we're going to go ahead and take a log base 9 of both sides. And what that helps us do is that helps us isolate x. So log base 9 and 9 to the x, and 9 are inverses of each other. So we get log base 9 of 21. And that's our answer for the non-calculator portion. Moving on. This right here is e to the x. So what we're going to do is take a natural log or a log base e of both sides. So remember in math, log base e, which is 4 letters, converts to 2 letters with natural log. Natural log and e, which is considered the natural number, are inverses of each other. So this just ends up being the natural log of x. Now we got a couple more steps on these ones. This is base 2. So what we're going to do is make sure that when we reverse base 2, we do it with the logarithm of base 2. So you can see what I'm really doing is this piece is here, and then I'm taking a log base 2 of both sides. So then 17 ends up here, and you can see that there's a log base 2 of both sides. That's nice because this log with a base 2 undoes that exponential with a base 2. So then I have m minus 5 equals log base 2 of 17. The n is not by itself yet, so I'm going to add 5 to both sides. When I do that, I'm going to make sure to put parentheses around the argument of the logarithm, because the 17 belongs to that log base 2, but the 5 doesn't, so they're not like terms, so I cannot combine them. Moving on. Oh, this one is also base 2, so I'm going to do that again. Log base 2 of 2 to the 9x equals log base 2 of 85. Don't try to shortcut this. Make sure you're doing proper form. That log base 2 undoes the exponential of base 2, and then I'm left over with 9x equals log base 2 of 85. Divide by 9 to get the x by itself. We're reversing that multiplication. And that's the same thing. I believe the answer key says this. So dividing by 9 is the same thing as multiplying by 1/2. Moving on, I'm going to try and get these last ones done. My kiddos are being wild. This says, use the property of equality to solve each of the equations below. So it's telling you use the property of equality. It's not telling you to use a logarithm. So what we're going to do is see that we have this left side has a base of 9 and the right side has a base of 3. We need them to have the same base. So I'm going to change 9 to 3 squared. And then I have x plus 1 left over. Make sure you put that in parentheses because that means you have 2 terms, which means that distributive property is going to apply. Because we have 2x plus 1 equals 3 to the 5th. What we're saying now is because the bases are equal, this is that property of equality. We don't really need to focus on the bases anymore. We just need to focus on the, let me reverse this a few steps because I just caught my mistake, silly goose. Right there. When I distribute, this is 2x plus 2. Not 2x plus 1 because that 2 gets multiplied to both the x and the 1. Those are irrelevant. And then we're just going to solve this part. Just reversing everything to isolate the x. So we get x equals 3/2. This last one. we're going to see that we need to write 32 and 16 with the same base. 32 is 2 to the 5th power, but then we have that 3x right there, also in the exponent. And then we see that 16 is 2 to the 4th power. Again, these bases have to match. Now that they match, we can just solve the exponents. 3x times 5 is 15x. And this side only has a 4. So we get x equals 4 over 15. Okay, and that's that piece. Alrighty, let's go ahead and flip that paper over. And the next problem says to exponentiate to solve. And we talked about this in class that you can exponentiate to solve these, but we can also use the property of equality with these particular ones because they both have the same base. So this is log base 5, then there's an equal sign, and then there's log base 5. So that's using the property of equality. So what we're saying is because both of these have log base 5, those are equal. So we can kind of say they already meet the condition of equality. And we can go straight for the negative 3x equals 21. Isolate the x. And we get x equals negative 7. Okay, then we move on to the next one. And again, you could exponentiate these with log base or with base e, but because both of these have that natural log there and the equal sign in between them, we can just say because these are both the same natural log with the same base, then we can conclude that if we get their arguments to be equal, then the whole statement will be equal. So then I'm going to subtract 3x because you get the variable on one side first. This cancels out. And then add 7 to both sides. And then we'll divide by 2. And that gives us x equals 5. And you can actually plug these both in for x to see that they are in fact equal. 5 times 5 is 25 minus 7 is 18. So it's the natural log of 18. And 3 times 5 is 15 plus 3, which is also 18. So you can see that they're equal. Let's go ahead and take a look at the next one. Again, the directions for this one were to exponentiate. And because we have two logarithms on the same side of this equal sign, we're going to need to condense them down to a single logarithm using the same method that we did in problems 4 and 5. So what we're going to do here is we're going to notice that this is subtraction, so we're going to use division, and then we're going to condense it to a single log, so we don't need that piece. So what we have is log base 2 of 3x, and then for this divided by symbol, we use a fraction bar of 5 equals 2. How do you reverse a logarithm? It told you in the directions to exponentiate, so that means put your equation in the exponent, and what you do to one side, you do to the other. So that big 2 became a mini 2, just like this came up in the exponent. Then we know that exponentials and logarithms are inverses. So we have 3x over 5 equals 2 to the 4th power, which is 4. And then from there, we can just use reverse properties. This is dividing by 5, so we're going to multiply by 5. And we get 3x equals 20. Divide by 3, divide by 3, x equals 20 over 3. Okay. Same thing for the next one, except for now we have addition. So we're going to change that to multiplication. And we're going to cross out the other logarithm because we're condensing. So we have log base 6 of x plus 1 times 4 equals 1. To undo this logarithm right here, we're going to go ahead and exponentiate. So we're just going to take that entire statement and put it up in the exponent. I'm moving this 4 to the front because that's standard. I'm going to see that these undo each other, the 6 and the log base 6. So I get 4, and then I'm just going to do that math. 4x plus 4 equals, and 6 to the first power is 6. So that gives us 4x plus 4 equals 6. So then we subtract 4 from both sides. We get 4x equals 2. Divide both sides by 4. X equals 2 over 4, which equals 1/2. So our answer for this one is x equals 1/2. Okay, moving on. All right, divide, cross that out. So then we get natural log of x minus 5 using the fraction bar for that division symbol equals 3. How do I undo a logarithm? I raise it to the exponential with the base. So that case, if it's natural log, it's log base e. These undo each other. So I have x minus 5 over 9 equals e to the third. This is on the non-calculator portion, so I can't type in e to the third in my calculator. So all I'm going to do is get the exact solution. So I get x minus 5 equals 9 e to the third because I just put that 9 in the front. Whoa. And then I'm going to put that 5 at the end, and I get x equals 9 e to the third plus 5. Okay, moving on. This is actually from section 10.2, just so you're aware, because it says properties, and that's where we learn the properties. So basically, we know that log base 3 of 5 is 1.465. And then they also know that log base 3 of 6 is 1.631. So we have to try and manipulate A, B, C, and D to either use one of these numbers or both of these numbers. And because it says properties, we're going to be really careful with that. So remember, that's dividing, and dividing is a minus. So again, dividing is a minus. So we're going to go ahead and go log base 3 of 6. Then we bring in that minus, and then we have log base 3 of 5. So now, if you notice, we can put that there and that there. So log base 3 of 6 is 1.631, and then minus the other one, which is 1.465, and I have no idea what that is, and I don't have a calculator with me, so you're just going to go ahead and have to make sure you plug that into your calculator to get the approximate answer. Okay, the next one, log base 3 of 25. Well, we're only given log base 3 of 5 and log base 3 of 6, so what we're going to do is we are going to be creative here and change 25 to 5 squared, which will then let us bring this 2 down in front, which will give us 2 log base 3 of 5. And if you look right there, we have one of the pieces that they gave us up here. So now all we have to do is 2 times 1.465. And that'll give us our answer. Again, I don't have a calculator with me right now, so you'll have to fill in that blank. Okay, moving up to the next one, log base 3 of 30. they did not give us log base 3 of 30. They gave us 6 and 5. So you have to figure out how to use those two numbers to get what you need. And if you notice, 6 times 5 is 30. And then what you can also notice is that when we use properties of logs, if we do log base 3 of 6 and we expand it, the multiplication becomes a plus, and then we have log base 3 of 5. So now all we have to do is substitute the values that they gave us, 1.631 for log base 6 of 5, and then we have 1.465 for log base 3 of 5. And then, like I said, it's your job to plug that in your calculator on the test to get the answer. For the next one, we have log base 3 of 1 over 6, and we know that that's 6 to the first power, so it's going to be log base 3. We're going to take that and move it up, so it's going to be 6 to the negative 1. Then we're going to go ahead and take that negative 1 and move it in front because it's an exponent. So we have negative log base 3 of 6. And if you notice, there's that log base 3 of 6. So we just need to times it by negative 1. And I don't need the calculator for that because that is approximately negative 0.1631. All right, let's go ahead and finish this up. So we are up here at the top. Example 11 says to solve each exponential equation using logarithms. So there's a clue for you right there that you're going to need to use a logarithm, and then to approximate each solution to 3 decimal places. So this just means it's going to be in the calculator. So first thing we're going to do is divide both sides by 9 to isolate the exponential. And a negative divided by a negative is a positive. So that's where we get e to the x equals 16 over 9. Next, because this is e, we're going to take the natural log of both sides. So we get that right there. And then the natural log undoes the base e, and we get x equals natural log of 16 over 9. And then you're going to plug that into your calculator and get an approximation. Alrighty, next for b, we're going to first isolate the exponential. So that is that piece right there. So we're going to subtract 3 from both sides. 12 to the negative 2x equals 11. And then we're going to take a logarithm of both sides because the exponential is base 12. It only makes sense that we use a logarithm with that same base. These undo each other, and we get negative 2x equals log base 12 of 11. And then we're going to divide both sides by negative 2. And we get x equals log base 12 of 11 divided by negative 2. And then again, you're going to plug that in your calculator to get your decimal approximation to 3 places. The pattern just continues. Again, we have this right here, 20 to the x plus 10. We don't have to divide anything out because the base is already isolated. So what we're going to do is take a logarithm of base 20 of both sides. And then this log base 20 will be undoing 20. And then we'll just have x plus 10 equals log base 20 of 83. We'll subtract 10 from both sides, at which point we'll put parentheses around our argument so we do not accidentally combine the argument with a constant that is negative 10. You cannot combine them. And then we'll use our calculator to figure that guy out right there. The last part of this test and worksheet and unit is to exponentiate, to solve these equations. So again, they start with the logarithm, so it makes sense that we're going to put both sides of this equation into an exponential with a matching base. Those undo each other, and we're left with x minus 4 equals 2 to the third power, which is 8. And then we're going to add 4 to both sides, and we get x equals 12. We don't even need to plug that into our calculator because it's a nice integer number. For this next one, we have the natural log of 7x equals 1. So to undo the natural log, we're going to use the reverse of that, which is base e. And what we do to one side, we do to the other. And then we recognize that e and natural log are inverses of each other. So we get 7x equals e to the first power. You don't have to write the 1, but you can. And then we divide both sides by 7. So we get x equals e over 7. And then you can plug that in your calculator to get your decimal approximation. And that is all for Chapter 10.